Welcome back, physics enthusiasts. Let's do multiple choice question on topic current electricity. Again, the questions are really good for your last time revision. Let's begin with that. Okay, so your first question is the resistance of a metal wire increases with increasing temperature on account of. Okay, so resistance with temperature has a dependence from resistivity. The formula of resistivity is m upon ne square 2. So basically, when the temperature is increases, the collision between the electrons also increases and the time duration between each collision decreases. That is, your relaxation time tau decreases, which increases the resistivity. So if resistivity increases, resistances increases, and this is due to decrease in relaxation time. Okay, there will be change in electron density, but electron density is increases. So the increase in resistivity is because of decrease in relaxation time. Okay. What happened with number density is basically free electron density increases because the bonds break. Increase in mean free path, no, there will be decrease in mean free path because the collision become rapid, time decreases, the distance between them also decreases. Increase in mass of electron ऐसे नहीं होता. The dimensions of the blocks are 1 centimeter, 1 centimeter, 100 centimeter. If specific resistance of its material is this, then the resistance between the opposite rectangular faces. So for the rectangular faces, you have to take this area, then the length will become 1 centimeter. Use simple formula of resistance, which is rho L by A. Rho here is 3 into 10 raised to the power minus 7. Length, you will take 1 centimeter. 10 raised to the power minus 2 meter. And area is L into B is 1 into 100 into 10 raised to the power minus 4. 100 and minus 4 will be minus 2. You can consider back this minus 2 and you left with 3 into 10 raised to the power minus 7 ohm. Very simple. Okay, so resistivity of a given conductor depends on temperature, length of conductor, area of cross-section, shape. It only depends on temperature and the material of the conductor. For length and area, it's the resistance which depends on length and area, but the shape of a conductor doesn't matter. Next. Okay, so in the next question, a cell of EMF E and internal resistance R is connected across a variable external resistance R, the graph between V and R. देखो simply जो potential होता है that is V is equals to IR and I can be written as E over R plus R into R, and you can also write this as this. We divide both numerator and denominator by capital R. Now you can see that as R increases, V also increases because it's in reciprocal. So this remain constant, no, and this has inverse relation, no. So these two will work. But if your R tends to infinity like this, then V is almost approaching to E because small r by infinity gives you 0, 0 plus 1 is 1 and it is almost equals to E. So if R is moving towards infinity, V approaches E. And when R tends to 0, when R is 0, then that small r by 0 is infinity, infinity plus 1 is infinity, and E by infinity is again 0, then V is also 0. So R is 0, V is 0, this B is the appropriate graph. Next, in a Wheatstone bridge, all the four arms have equal resistance R if the resistance of the galvanometer arm is also R, the equivalent resistance. This is R, this is R, this is R, and this is R. So this is basically a balanced condition because the ratio is same. So in the balanced condition, no current flows through this galvanometer, and basically basically this behave as a series combination. These two resistance are in series and these two resistance are in series, and then they are in parallel. So R plus R is 2R, this is 2R, and then parallel is 1 by 2R plus 1 by 2R is 2 by 2R, that is R simply. So A is the correct option. Simple maths. Series में हो जाएगा R plus R, that is 2R, and for the parallel R equivalent is as a formula of 2R into 2R plus 2R plus 2R. So 2 2s are 4, R square by 4R, this simply R. R1 into R2 upon R1 plus R2, this formula. Okay, the next is consider a current carrying wire in a shape of a circle. Note that as the current progresses along the wire, the direction of J changes in the exact manner while the current I remain unaffected. So the current density is equals to I by area, current per unit area, and J also has a formula of sigma E. It has two formulas. So what factors are responsible for that? Source of EMF? No. Electric field produced by charge accumulated on the surface of wire? Yes, because it depends on electric field. The charge just behind a given segment of wire which push them just the right way by repulsion? No, the charge is ahead. No. So it depends on area since I is constant and I remains unaffected. So it depends on area and electric field. So B could be the option. Next, two batteries of EMF E1 and E2 and internal resistance R1 and R2 respectively are connected in parallel as shown in figure. Okay, तो हमें condition check करनी है that equivalent is greater than E1 less than E2, equivalent is smaller than E1, equivalent is E1 plus E2, and equivalent is independent of internal resistance. Okay, so basically as per the definition, derivation, you know that E equivalent is equals to E1 R2 plus E2 R1 over R1 plus R2. This is the formula of equivalent in parallel combination. Now, we can do, it is given that, its formula is E equivalent is E1 R2 plus E2 R1 over R1 plus R2. Okay, now you have given that E2 is greater than E1, right? I'm trying to make this formula. Let's multiply R1 both the sides. Okay, then add E1 R2. E1 R2 both the side plus E1 R2. So this was E1 R1 and you are adding E1 R2. So from here you can say that E2 R1 plus E1 R2, here E1 can be taken as common and R1 R2 can come down, is greater than E1. So this is basically your E equivalent. So E equivalent is greater than E1. First thing. So E equivalent is smaller than E1 is wrong. Next, E equivalent is given by E1 plus E2 is also wrong because you can understand from this formula it is not equals to E1 and E2, and it is also not independent of R1 and R2 because R1 and R2 are there in the formula. So it is greater than E1 and it is obviously less than E2 because E2 is greater than E1. So A could be the appropriate answer. Okay. So I have just used the linear thing. Linear inequality thing. Next, the drift velocity of a free electron in a conducting wire carrying current I is V if in a wire of the same metal but of double the radius the current be 2I. Then the drift velocity of electron. So the relation between I and drift velocity, which is very important relation, is I is equals to NEA VD. Okay, now what they are saying that the current is double. Let's take the current to be 2I. And the radius is also double. So NE, if radius is double, then the area becomes 4 times because it is pi r square. So let's take it as simply 4a, and we have to calculate new VD dash. So it's 2y over 4NEA. 4NEA is equals to VD dash. This is 2I upon NEA is your old VD and EA. So your new VD dash become half of old drift velocity. Okay. Next, the element of a heater is rated P by PV. If it is connected across a source of voltage V by 2, then the power consumed by it. Okay, so it's given that the element of a heater is rated PV. If it is connected across if it is connected across a source of voltage V by 2. See, the power has a formula of VI or I square R or V square by R. So here it is rated with voltage. So we will use a formula of voltage here. So power is equals to V square by R. Now the voltage is half. So new power become V square by 4 R. That is 1 by 4 times of P. That is option number D. Okay. Next, you have to check that you see for a particular physical quantity you have 2 or 3 formulas, and whatever the constants or whatever the variables have been given, you have to choose the formula accordingly. If in this particular question I is given, then I can use I square R, and if I and V given, then I can use VI, but here it is given a voltage, so I use VI. And why not VI? Because the element of the heater is same. So the resistance of that particular heater is same. It is not changing. Its area, length, and everything is remain changed. Just the voltage change. So that is why I use V square by R, because R remains same. There is no change in temperature. Nothing has been mentioned here. So just choose the formula wisely. What variables are constant, and in which term you have to calculate the relation. Next, question number 10 says a metal rod of length 10 centimeter and rectangular cross section of 1 centimeter into half centimeter is connected to a battery across opposite faces. The resistance, you know, the resistance is basically rho L by A. So it is inversely proportional to A. You have a dimension of 10 into 1 into half. So the smaller would be A, the larger would be R. So it is maximum when the area is this. So area should be minimum. So A is the appropriate answer. Which of the following characteristics of electron determines the current in the conductor? Basically, in the conductor, it's I is equals to NEAVD. So the drift velocity gives you the current in conductor. If it is given semiconductor, then you can use thermal velocity as well. Okay. Next. Temperature dependence of resistivity of semiconductor, insulator and metal is significantly based on the following factor. So resistivity rho has a formula of M upon NE square tau. So number of charged carrier can change with temperature T. Yes, it can change. It increases. Time interval between two successive collision can depend on temperature. Yes. Length of a material can be function of T. No. Mass of carrier. No. So A and B are the appropriate ones. Okay, so in the next question, you have a cell of internal resistance R is connected across an external resistance capital R can supply maximum current. So your current is basically I is equals to E over R plus small r. Okay. So for the maximum current, the denominator should be less. So I can check with hit and trial method. For R to be equals to R, your I is simply E by here I is equals to E by 2R, right? Now, if R is very, very greater than capital R, then obviously your denominator will increases very much because capital R is increasing so much. So I will be less than the first one. because your R is increasing. So if you're increasing the denominator, then your numerator will decrease. It's an inverse relation. For R by 2, I is equals to E over small r is 2r, 2r plus r, 3r. And if R0, so this is a condition of short circuit, then there would be no current, and I would be E by small r, but R0 will gives you that short circuit thing. So in the appropriate thing from this and this, I think 2R is less than IB maximum. So R is equals to external resistance should be equals to internal resistance. Next, Kirchhoff junction rule is a reflection of conservation of current density vector, conservation of charge. Yes. The fact that the momentum with which a charged particle approaches a junction is unchanged as a charged particle leaves the junction. The fact that there is no accumulation of charge, there is no accumulation of charge at the junction also. These two are the. Okay, the ratio of the current density and electric field. J is equals to sigma E. So J by E is equals to sigma, which is conductivity. It's important. This J is equals to sigma is basically the vector form of Ohm's law. V by I is equals to R is the scalar form of Ohm's law, and this is a vector form of Ohm's law. Electrical resistance of a conductor R varies directly proportional to its area of cross section. No. Decreases with increase in temperature. No. For conductor it increases. Decreases with increase in its conductivity. Decreases with increase. If sigma decreases, then resistivity increases, then resistance also increases. So if conductivity increases, let's take it opposite, sorry. They are saying if with increase in its conductivity, if sigma increases, then resistivity decreases, then resistance also decreases. So C is the thing. Independent of its shape but depend only on its volume. Independent of its shape but it doesn't depend on the volume as well. Okay. So C is the correct one. For a fixed potential difference applied across the conductor, the drift velocity of free electron does not depend on for a fixed potential difference. So Vd has a formula of EEM by tau, and electric field can be written as V by L. So if the potential difference is same, then the drift velocity of free electron does not depend on free electron density and mass of the electron. It is there, length of the conductor, and temperature has a relation with relaxation time. So I think free electron density of the electron can be the thing. E can never change. E can never change in any condition. E remains invariant. Okay, now two sources of equal EMF are connected in series. The combination is in turn connected to an external resistance R. The internal resistance of two sources are R1 and R2 if the potential difference across the source of internal resistance R2 is 0. Okay, so you have two equal EMF E and E connected in series. The combination is then connected to an external resistance capital R. It has an internal resistance of R1 and R2. If the potential difference across R2, this V, is 0, then R is equals to what? Okay, so that V is equals to what? E minus IR2. And if this V is 0, you can calculate I. I is EMF upon my total. So total EMF is 2E. R is R1 plus R2 plus this external resistance R. Then if V is 0, then it is E minus 2E R1 plus R2 plus capital R into R2. Then your E can shift to the other side. You can cancel E, then it becomes R1 plus R2 plus R is equals to 2R2, and this capital R is equals to 2R2 minus R1 minus R2, and this is simply R2 minus R1. So B is the correct one. Okay. Okay, so the next question is if N, E, tau, M have their usual meanings, then the resistance of the wire of length L across R is equals to rho L by A. Rho is M upon N E squared tau A L. Adjust the formula. 2022 में पूछा गया है, just the formula. The formula of current electricities are really, really very important. So you have to remember all the relation. Okay, next. A straight line plot showing the terminal potential difference V of a function of a cell as a function of current and internal resistance of the cell would be. So V is equals to E minus IR. E is the maximum potential. That means the potential when the current is 0. So when the current is 0, potential is 5.6. The EMF is 5.6. Now take value of V at any point, and for that we can take the value of I. So if it is 4.2, then the value of current is 0.5. So this is 4.2 is equals to minus 0.5 times R. Then 4.2 minus 5.6 is equals to minus 0.5 R. 12 minus 6 gives you 6. Okay. Okay, sorry. 6 minus 2 is 4. It's 1.4. Okay, minus 0.5 R. So then R is equals to your 14 by 5 directly. 5 2s are 10. 4, 5, 8s are 40. So it's 2.8 ohm. Okay. The car battery is charged by a 12 volt supply. The energy stored in this, the charge passed through the battery is. Energy is given, but we know that work done is equals to charge into del V. So charge is basically work, and you can take it as the energy. 5 over potential is 12. 10, 12, 6 are 4. 6 into 10 raised to the power 4 coulomb. A is the appropriate answer. We use alloy for making standard resistance because they have low temperature coefficient of resistivity and high specific resistance. Just remember this. So is the correct one. Next. Okay, so in the next question, if the potential difference V applied across a conductor is increased to 2V and the temperature remain constant, the free electrons in a conductor. So now the voltage is increased, then let's take VD, which is EE tau by M, and that E can be written as V by L. So you can write it as V by L into tau. Now if voltage is double, then VD is also double. So new VD dash is equals to twice of VD. Now VD also has one relation. I is equals to NEAVD. So the VD is I over NEA. Now the temperature remains same, so N will remain same, area is not changing, and E is also constant. But V is equals to IR. If V is double, then I is also double. I is double, VD is double, then your N, number density, should remain same. So it should remain the same. Okay. Next, a battery is connected to a conductor of non-uniform cross-sectional area. The quantities or quantity which remain constant is. Okay, so battery is connected to a conductor of non-uniform. So the quantities and quantity which remain constant, drift velocity will change. Drift speed will change, and if VD is changing, then E is also change because it has a relation. So electric field will also change. So the current will remain same only. Okay. For a metallic conductor, the correct representation of variation of resistance R with temperature T is, it increases with temperature. So this is the correct representation, which in this particular part gives you residual resistivity. Okay. This will increase, this increase, but this is the accurate one. A steady current flows through a metallic wire whose area of cross section A increases continuously from one end of the wire to the other. The magnitude of drift velocity of the free electron is a function of A. As inverse relation, I is equals to NEAVD. So VD is equals to I over NEA. So current is steady, cross-sectional increases continuously, so it will decrease. And how it will decrease? It decreases like this, linearly. Don't go this, okay? Because this shows that when area is 0, then VD is 0. But it's not like that. It goes to infinity. So this is the appropriate one. Next, a conductor of 0.8 ampere flows in a conductor of 40 ohm for 1 minute heat. I square RT, simple. I square RT. I square is 0.8 into 0.8. R is 40 and time is 1 minute, that is 60 seconds. 10, 10, 8, 8 is 64 and 4, 6 is 24, 4, 4 is 16, 4, 6 is 24, 25, 2, 4 is 8, 2, 6 is 12, 6, 10, 1506, 8, 9, 10, 11, 12, 13, sorry, 1536, that is B. Okay. A cell of EMF E is connected across an external resistance R. The current I is drawn from the cell. The potential difference across the electrodes of a cell drops to V. As the internal resistance has the relation of this, you can simply learn it. It has this relation. You can derive it as well, but you can learn it. It's a direct formula. Next, the current density due to drift of electrons in a conductor is given by the symbol. Current density I is equals to NEAVD. I by A is J is equals to NEVD. Like this. Okay. Okay, let's derive the question 29. A cell of EMF E is connected across an external resistance R. When current I is drawn from the cell, the potential difference across the electrodes of the cell drops to V. So you know that V is equals to E minus IR, and I is equals to EMF upon R plus small r into R. Okay. So here you can take E out, and this become 1 minus R over R plus R, and then V by E is equals to R plus R. You take the LCM, fine, and just reciprocal it. You'll get this. Then this is 1 plus R by R. Go take 1 there. This is E minus V by V into R, which is equals to small r. So this is the relation. Okay. E minus V by V. E minus V by V by R. But just remember it. If your concepts are like bang on, then you can derive anything from anywhere. And if you just remember the basic principle, the basic formula, then there is no problem with you. And if you are good with remembering things, then you can learn as much formulas as you can. And the other direct relations you can just put. And yeah, it saves the time, definitely. So it's up to you how your brain process the things. It processes the concepts more, or you can memorize the things more. So it's your strategy, it's your technique to score good. Okay, so that's all with current electricity, and thank you for watching this video. Do like, share, subscribe, and give me your comments, feedbacks, and we'll meet you in the next video.